Okay, I'm going to go over 3 of your problems from tonight's homework. The first one was number 6. I wanted to do this because it's a little bit different from the M&M example that we had done in the notes. And that was number 4. So a salesman who is on the road visiting clients thinks that on average he drives the same distance each day of the week. He keeps track of his mileage for several weeks and discovers that he averages 122 miles on Mondays, 203 miles on Tuesdays, 176 miles on Wednesdays, 181 miles on Tuesday, and 108 miles on Fridays. He wonders if this evidence contradicts his belief that in a uniform distribution of miles across the days of the week. Explain why it's not appropriate to test this hypothesis using chi-squared good as a fit. Well, that usually means we need to look at the conditions. The first condition is data is in counts of a categorical variable, and miles driven, especially the average miles driven, is not categorical. So it's not appropriate to use a chi-squared test. Let's look at number 27 now. It's common folk wisdom that drinking cranberry juice can help prevent urinary tract infections in women. In 2001, the British Medical Journal reported the results of a Finnish study in which 3 groups of 50 women were monitored for these infections over 6 months. One group drank cranberry juice, another group drank lactobacillus drink, and the third drank neither of these beverages, serving as a control group. In the control group, 18 women developed at least one infection, compared to 20 of those who consumed the lactobacillus drink and only 8 of those who drank cranberry. Does this provide supporting evidence that the value of cranberry juice in warding off urinary tract infections? So the first question it asks us, let's make some space here, is this a survey, a retrospective study, or an experiment? And explain, and this is an experiment because they are controlling the treatments. So they're applying it and saying, okay, we're going to randomly assign you to groups, and then you're going to take this drink, you're going to drink this, you're going to drink nothing. So it's an experiment. So the next question is, will you test goodness of fit, homogeneity, or independence? We're going to test homogeneity because we are looking at one thing amongst a group. We're looking at whether or not they are going to have at least one urinary tract infection, and we have several different samples. So this is homogeneity. So homogeneity. Oops, I put that in the wrong spot. That's the answer for that one. State your hypotheses. So our hypotheses are going to be that the 3 treatments for urinary tract infections are the same, and our alternative is going to be that they're not the same. I'm going to pause it and type them out so then you can see them. Okay, so there you see I've written it down. Our null hypothesis, the treatments for urinary tract infections are the same, and the treatments for urinary tract infections are not the same. So we'll test our conditions next. I'm going to do this in pen over here. And in order to do that, we kind of have to put our data together. It's given to us in a big paragraph. So the data is counts. The experiment was randomized. And we need to know expected counts. In order to do expected counts, we have to know our actual counts. So we have cranberry juice, that group. We have the lactobacillus group, and then we have the placebo group. Those are our 3 groups. And then here we have greater than 1 and 0. So those are your options, right? And these should all add to 50 because we had 50 people in each group. So it says that in the control group, 18 women developed at least one infection. So for the placebo group, 18 had one infection, and that makes 32 had no infections. Compared to 20 of those who consumed lactobacillus. So in the L group, 20 had at least one, and 30 had none. And then only 8 in the cranberry juice group, so 8 and 42. So now we need to find our expected counts. We can do this by plugging this all into the matrix. So we're going into matrix, edit, and then edit matrix A. Put your data in. You do not put in your totals. So you're only going to put in those numbers, and then we'll do the chi-squared test, and then we'll go back into matrix, edit, and then we'll look at matrix B. Those will be our expected counts. Okay, when I do that on my calculator, I get 15.33 for all the top ones. And I get 34.67. For the bottom one. We're going to continue that on this slide. So 15.33 and 34.67 across the board. Let's talk just a little bit about how to do it by hand. So we need our column total over our table total times our row total. So we need a row total, 28 plus 18, so that's 46. So we're looking at 50 divided by 150 times 46, and that is what gives us the 15.33. So that's how you would do that one by hand. And the other one would be 50 divided by 150 times 104, which gives us the 34.67. So that's how you would do it by hand. But we pretty much only ask that on multiple choice questions. Some free response will actually ask you to show how you got the expected value for a certain one. So how many degrees of freedom are there? We're on part E. There's cover up a row, cover up a column, and we end up with 2. So degrees of freedom is 2. And that you can also get by doing 2 minus 1, rows minus 1, times columns minus 1. Okay, part F says find chi-squared and the p-value. So now I'm going to go back into my calculator, stat, test, chi-squared test. So just see what this calculator is, and my chi-squared is 7.776, and my p-value is 0.0205. So then we're going to state our conclusion. I'm going to pause it, type it out, and then come back and talk over it. Okay, so my conclusion, since my p-value of 0.0205 is less than my alpha of 0.05, I reject the null hypothesis. There is enough evidence to convince me the treatments for urinary tract infections are not the same. And then for part H, that requires us to look at the individual components and take the square root of them. So you would take the square root of the individual components that you get listed after you do the test, and you see which one is larger. And what you're probably going to find in this one is that the cranberry juice has higher residuals than the other ones, standardized residuals, and that's gives us a clue that cranberry juice is the reason they're not the same. Okay, number 29. A poll conducted by the University of Montana classified respondents by whether they were male or female and a political party. So that's two variables they were looking at, and they did one sample. We wonder if there is evidence of an association, that's a clue, between being male or female and party affiliation. So both of those clues lead us to the independence test. So when it's two different variables, so they asked one sample, whether they were male or female, and then political party, and then it asks of an association. That's an independence test. So our null hypothesis is political affiliation is independent, or we say political affiliation has no association to gender. So you don't need to say them both, but you need to start realizing that when it asks about association, independent means no association. So the null hypothesis, if you're using those vocabulary words, is no association. And the alternative hypothesis would be that there is an association. Political affiliation is not independent of gender, or political affiliation is associated with gender. Then we look at our conditions. The data is in counts. This sample is random. Expected counts greater than 5, so we need to check that. I just typed this all out so you don't have to pause and wait for that. So let's look at what our expected counts are. I did it in the calculator again. So remember, we go to second matrix. We go over to edit, and then you edit matrix A. You change it to a 2 by 3, which it should still be from the last problem we did. And then you go in and do the chi-squared test. And then you go back into the matrix menu and you look at matrix B, which is our expected counts. And that is 43.66, 40.3, 4, 40.55, 37.46, 20.79, 19.21. And you make sure to write those down in the order that it is the table, so you don't have to relabel your table. But you do have to write them down as proof that you checked that condition. So since conditions are met, a chi-squared model is appropriate. I will use a chi-squared test for independence. And the only reason I'm spelling out the word chi is because I don't have a button on my laptop or my iPad for that. And I forgot to write that on the last problem, so you should go back to number 27 and write that in since conditions are met. I will use a chi-squared test for homogeneity. So now we're going to find the p-value, so we write down chi-squared in our p-value from our chi-squared test, and that is 4.85 is my chi-squared. And we just go into stat, tests, chi-squared test, and then hit enter. It calculates degrees of freedom for us in this one, 0.088, 0.088. And then we're going to state our conclusion. And here's my conclusion. Since my p-value of 0.088 is greater than my alpha of 0.05, I failed to reject the null hypothesis. Okay, so remember it's greater, so we failed to reject. There's not enough evidence to convince me political affiliation is not independent of gender. This is my HA. It's only my HA in the chi-squared test. In the other test, you would say not my null hypothesis, or you would restate the question. You could restate the question here as well. All right, I hope that helps. You can do the other two problems without me.